Hello, everyone. Welcome back. So at the end of last class, I haphazardly introduced a very important concept, dynamic memory allocation, and kind of sort of started to use it to improve our strings example, broke it in the process. Today we're going to go into way more detail about that and finish what we started. So yeah, by the end of today's lecture, you should be able to use dynamic memory allocation in C. This is also the cutoff for things that will definitely, absolutely be on the test. Try and think of practice questions for yourself because I'm apparently not allowed to share past midterms. But after we're done talking about dynamic memory allocation, I'm going to move on to sort of the next major concept in the course, which is design by contract, which is basically getting a set of statements that need to be true before a function executes, after a function executes, and all the time. Think of it like in a mathematical sense, really. And basically that makes programming errors easier to avoid in languages that don't have very robust safety features, such as C, and debugging way easier in every language ever. Like, I've never used design by contract in a practical scenario, but I think like I'm using design by contract, which will make sense later. So dynamic memory allocation, definitely on the test. Design by contract, it depends. This lecture is like super long, and I don't expect to get through the entirety of it today. I expect to finish it up tomorrow. And how far we get into design by contract will determine how much that will be on the test. So, dynamic allocation. Actually, before I get into this, let's just log back into Aviary and check out the string example so we can see what state we left it in and sort of motivate what we're talking about with dynamic allocation. So we already have the object file for the string that compiled successfully. And then when I try to compile the main file, also with this compilation command, you might be thinking that later on, when we get a whole bunch of different objects and just parts to programs, this will get kind of unwieldy. And yeah, it does. We'll discuss a way later on how to sort of automate the process of typing out these commands and managing dependencies. Yeesh. So we made a big deal last class about how great and awesome it is to hide implementation details and how much easier it's going to make your life and all your coworkers' lives. But now main doesn't know what a string is. It knows that a type string exists, but it's impossible to instantiate it because it doesn't know about the struct definition in string.c, doesn't have access to this. So what are we going to do about it? Dynamic allocation. So yeah, like I just said, hiding implementation details is great, but it kind of broke our code. So we can't instantiate the, almost said class, can't instantiate the struct the normal way. We could return a pointer because it turns out you could have a pointer to a struct without knowing anything about that struct. Main.c would just have a memory location of a string struct, and then that would be great, question mark? But how do you get it? You might say return the pointer from make string. You might say that if you're a doofus who does bad programming practices. And yeah, if you tried that, you'd run into stack corruption, which will be on the test. And to avoid stack corruption, we need to take advantage of the other big region of memory. We're not going to mess with the code section ever, unless we just, other than writing code. But anyway, we need to allocate memory on the heap using malloc. So the malloc function requests an allocation of heap memory. So let's take a look at the man page. And you could see that really it's a family of functions that do different things. What we're most interested in is malloc itself, which takes a number representing how many bytes you want to allocate, and then returns a pointer to the allocated memory. Just rummaging through stuff to see if I can find that picture that I drew yesterday. Aha. Cool. So every variable we've ever declared so far in our code has been on the stack, but now with malloc, we're able to allocate memory on the heap. So what does that mean for us? It means that we could use memory that survives after a function returns, which lets us return pointers and do some of the pass-by reference stuff that you may be more familiar with from object-oriented programming. Before I get back to the presentation, the slides, I want to highlight a couple other things. One is that the return type for malloc, it looks like void, but it also has the pointer symbol. Kind of weird. Those things kind of contradict each other. We'll talk about this more later, but turns out malloc actually returns an instance of a type you haven't seen before, void pointers. Pointers don't generally encode information about the type of thing that they point to, but void explicitly states this is just a pointer to something. We don't know what it is, which is great for hiding implementation details. Additionally, free is going to be very important very soon. Since heap allocated memory isn't automatically cleared or automatically deallocated when a function returns, it is not automatically deallocated ever. And it's your job to free up memory that you allocate. If you forget to use free after using malloc, not only will you lose marks, but that's called a memory leak. And if you've ever had some software, especially a game or an operating system, because those are the most complicated things ever. If you've ever had one of those things slow down over time and eventually crash, chances are some programmer forgot to include a free corresponding to a malloc. So it takes the void pointer that you got from malloc, and then it deallocates memory so that other parts of your program can use it. I'm probably getting ahead of myself and will repeat myself on these slides. Oh well. Yeah, it takes a size in bytes. Oh, and it's going to get into a gotcha that I haven't mentioned yet. It returns either null or a pointer to a place in memory where that many bytes have been reserved for your use. Malloc can fail. All this memory allocation stuff happens at runtime, which means that your program and your operating system, I guess if you're using something like Java, your runtime environment, can't guarantee that there will be enough space on the heap to store whatever you want to store there. So when you're programming with malloc, it's good practice to check the value of the pointer it returns and then handle errors if it turns out to be null. So far this example at least, it's not very different from stack arrays. And the main difference so far is that it can and will fail. But the whole not automatically deallocated when a function returns thing is super advantageous for us. A really important consideration for using malloc is asking for the right amount of space, because it's dynamic, and you can specify the required space at runtime. This was kind of messy earlier in the course because there's some rules for how to specify sizes of arrays that have changed over the years. And when you're allocating space for arrays on the stack, the safest way to go about it is to just always use constants that are defined with #define, the preprocessor thing. And then variables sometimes work. You could sometimes define a stack-based array with a size based on a variable, but it's kind of dicey. With dynamic allocation, we can specify whatever we want based on whatever variable or user input or whatever at runtime. So yeah, to ask for the right amount of space, there are two things you need to know. How many things we want to store. This is most useful for storing arrays in the heap, but I guess when you're allocating a space for a single struct, how many things is one, but you still have to sort of keep it in mind. More importantly, though, you need to know how many bytes the thing you're allocating needs for storage. So for our string type, that'll require a specific amount of bytes. How many bytes does a char take? What about an int? Off the top of my head, I think it's 1 byte for char and 4 bytes for int. And then we have 500 chars in contents. So I don't know, 500 times 1 plus. Did I say 4? I might have said 8, whatever. I really didn't need the calculator for that. 504 bytes. So we can just say malloc 504, right? Nuh-uh. Remember from earlier in the course that each primitive data type has a vaguely defined size, and the C standard specifies how many bytes the type should take at least, but it doesn't define an upper limit. So int, for example, is at least 16 bits, but I'm pretty sure that on, no, I'm not going to argue that. I think 16 bits is pretty common, but it should be a bit of a red flag that I'm going like, oh, it uses at least as many. I think we need to be more certain. This links to that Wikipedia article that I really like. Very helpful reference if you're ever working like at the bit level. So yeah, different platforms use different amounts of space for different types. 16-bit ints are pretty common, but you shouldn't be surprised to see 32 or 64-bit ints. I think there are like some obscure platforms that use sizes that aren't a power of 2. I wish I could say you could probably ignore that, but this is programming practices. Your code's got to be generalized. So you can't predict how many bytes something will need at compile time. So we need a new tool to help us. We're going to use sizeof. It's a unary operator that tells how many bytes any specified data type requires. So a unary operator is something you've used before, I'm sure. It's just any operation that takes only one piece of input. Absolute value is 1, negation is 1, factorial, then like all the trigonometric functions are unary operators. We have some more from programming. And check it out, it's sizeof. So it totally looks like a function call, but pretending that that sizeof is a function might mess you up when trying to debug stuff. So just keep in mind sizeof is an operator, not a function. Oh my gosh. Yeah. So instead of saying the string pointer is like malloc 504, you could allocate exactly as many bytes as needed for the type by just passing, I'm pretending like it's a function call, by using the sizeof operator on the type. So let's get back to coding. We're going to fix our program. So for starters, I think the constructor here is kind of messed up. We just have a string pointer, my string, but we don't define it at all. That's undefined behavior. You should know what that is for the test. And in this case, the string pointer just points to something. It might be useful, might crash, might overwrite some important information, might segfault. You don't know. So let's malloc it. By the way, the name of the function is like a short form of memory allocate. Simple as that for now. Let's check out, well, this is a workflow that all of you probably have lots of experience with. We're just going to make small changes, try to compile, get new errors, make some changes, try to compile, get new errors repeatedly. Because I know for a fact string.c has at least one more error in it, and there are probably a bunch that I just missed. So yeah, let's try compiling stuff. Oops, forgot the -c to only compile it into a object file. Okay, so this error is complaining that our make string implementation doesn't line up with the interface. We can fix that by modifying string.h. Okay, this is one of the errors that I didn't see coming. Forgot to include the file that contains the definition of malloc. Oopsie. And then these three concern a bit of syntax that I'll get to after fixing the previous errors. So let's vim string.h and change the interface to contain a pointer, or to return a pointer. Ideally, interface changes like this should happen as seldomly as possible. I keep making the comparison. This is like building a library for other coders to use, or just a small part of a big application that your coworkers should use. Interface changes break other code, and that's what we're trying to prevent with the whole hiding implementation details thing. So it's necessary for us to make this change because we just discovered dynamic memory allocation. But yeah, if you do your job well, this shouldn't happen often at all. Okay, now we just need to include stlib and figure out what this dot notation error means. It's common practice, I think, to put these angle bracket includes above these quote includes, but really they could be in any order. So the compiler was complaining about these dots right here. And why is that? That's because the variable myString, it's not a struct anymore. Dot notation to access properties only works with structs. A pointer doesn't have a property called contents. It's just a pointer. It's just a number. So to fix that, we need to dereference the pointer. You hopefully remember from that pointer example a few classes ago. If you don't remember, it's on the course website, something pointers from last week. That to get the value that a pointer points to, you use an asterisk right before the pointer. And then I'm still not really liking this syntax. I don't really trust the order of operations in any language. I've gotten it wrong too many times to rely on it. So I love spamming brackets. Now, we don't have to look at the Wikipedia article for of C order of operations. Now that we have these brackets, we can be sure that we're accessing the struct pointed to by my string, and then accessing its contents field. So if I compile it now, we should get fewer errors. We haven't fixed these because I want to talk more about dot notation. But let's try compiling it. OK, those last two errors are just those last two property accesses. And notice that the suggestion it makes isn't to use pointer dereferencing and or brackets. It wants an arrow, which, as it turns out, is equivalent to dereferencing and making sure the order of operations is on point. Cool. This does exactly the same thing as this. I just wrote it out explicitly the first time because I wanted to show off what that arrow actually does. Hopefully it's a more satisfying explanation than you use arrows when it's a pointer. So I'm just going to add a quick comment onto that. Notation. And let's finally fix up dot length. No clue why it's an arrow. No clue why the stack equivalent is a dot for that matter. But I honestly kind of like how the way of accessing properties of a struct on the heap looks different from when it's on the stack. So you could tell at a glance at the code that you're working with heap memory instead of stack memory. And now return my string will return the thing that malloc returned, and that will survive, or the memory that it's pointing to will survive beyond the runtime of this function. So we win. Before we go, though, I want to do a bit of error handling because malloc might return null. So if my string equals null, we'll see a more elegant way of handling errors in C later, and it'll kind of be a discussion on how that differs from exceptions seen in more complicatedly implemented programming languages. But for now, let's just printf and then return some garbage. And then any function using makeString should probably check that the return value of makeString is null. I might not do that much error handling in this example, though, because you'll learn a nicer way later. But it's very important to know right now that malloc might return null if it couldn't find enough memory in the heap to be allocated. Need to include for printf. Cool. So let's try compiling main again. Don't think this will work. I'm pretty sure we still have some stuff in main that pretends that, or that assumes that the string is allocated on the stack. Yeah. Okay. Same dot versus arrow error from before. And again. So, oops. You might think that the solution to these cases is to just add the arrow, but we hid all the implementation details. The compiler will just keep complaining if we attempt to dereference the pointer into a specific type and access like its properties. And just from a programming practices perspective, we just shouldn't be doing this. The variables that are inside of the struct definition, they're essentially public if you define them on the stack, but we're all about hiding implementation details, and we want to make something that's basically equivalent to private variables. So the solution to this is something that probably brought you a lot of tedium in Java-based courses, and we're just going to do it again. It's getters. So we'll make forward declarations for these in the header as well. But let's just charge ahead with those headers. So I already forgot the definition. We need contents and length. Char star get contents. Takes a parameter of a string pointer because all these functions are for manipulating the data model of string. And then we just return contents. Easy. I totally admit this specific example is kind of self-defeating. We just exposed the entire sort of spec, the struct definition for string. But I'm sure you can imagine how in a more complicated data type, there are some things that you would want other people using your code to be able to access directly, and other things that you would want them to not have access to because they are to do with how the thing works and are subject to change, and also giving people access to that might complicate its usage. So I'm just going to haphazardly copy and paste this stuff into the H file. Vim does copy and paste weirdly. We saw yank equivalent to copy, and delete equivalent to cut, and paste, thankfully, equivalent to paste. Those are just Vim things. It uses Vim's clipboard. And once you close Vim, that clipboard is gone. There are ways to make yank, delete, and paste use the system clipboard, but I'm too lazy for that. I've got better things to do. I don't know if equivalent functionality exists on Linux and Windows, but on Mac, you can use the system clipboard in Vim using familiar keyboard shortcuts. So Command-C to copy, Command-V to paste. So we're just going to enter insert mode, Command-V, and the output's going to look a bit messed up, but it's going to get the job done. Woo! Yeah, those line numbers are just text on the terminal. So our crappy workaround for copying or for using the system clipboard to copy and paste between Vim instances, it got the line numbers. But cleaning it up should be less effort than remembering the exact interface in copying it. Plus, I'm sure most of you are using VS Code anyway and can actually copy-paste stuff. I'm a bit jealous. So let's just clean this up. DD, 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 DD. Insert and manually backspacing stuff. And then semicolons. OK. At this point, it should actually compile. I wouldn't be surprised if there's an error or two, though. Uh-oh. Oh, right. We never actually fixed those dot notation things. OK. Let's go ahead and replace myString with dot contents with get contents myString, and do the same with length. Keep in mind that it's totally fair game to know about these functions because they're declared in the .h file. They're part of the string types interface. OK, now it should work. Oh. Ooh. Implicit declaration of function get length. That's creepy.
There was get size.
Cool. So I don't remember what I used in the struct definition, so let's just make this consistent. OK, length is the word we should use throughout the interface. Thanks for that heads up. OK, will it work this time? Place your bets. Oh, probably have to recompile string.o to get that change in definition ready. Because when we're compiling main, it still sees get length and attempts to link it to an implementation, but our string.o file still just has an implementation for get size, and it doesn't know that it should be called dot length or get length now. Remember when I was talking about a way to nicely automate the build process? It'll solve problems like that. And you can imagine things about dependencies not being up to date being massive headaches in big projects with like dozens of different types, each with associated interfaces and implementations. Okay. Binary code for string compiled. And let's try main again. Oh my gosh. Woo! It's the exact same functionality as before. But now we have access to dynamic memory allocation, which will open up so many possibilities for hiding implementation details, and all your coworkers will love you, or more accurately, companies will hire you in the first place. So I consider this a win. And there's a bit of a digression here about dynamically allocating an array. We may as well. It works in pretty much the exact same way as allocating memory for an object. You just use malloc with the array size. And this makes our implementation a lot more elegant. We previously allocated space for 500 characters no matter what. If your string is fewer than 500 characters long, you're wasting space. If it's longer than 500 characters long, you're probably causing a buffer overflow. Let's not do that. So like the slide said, we're just going to change the char array into a char pointer. As always, it's basically the same, but not. In this case, we're using pointers over arrays in order to not specify the size until we absolutely have to. So I think we're going to allocate space for contents right here. How should we do this? Char takes up just 1 byte. So when allocating space for arrays, or when allocating space for strings, you can get results that just happen to be correct, but are sort of arrived at the wrong way and won't generalize to other types. So we're going to do a sort of pointless multiplication by 1, but just for the sake of forming good habits. So size of char, this is just 1, but for types that take up more than 1 byte, which is almost all of them, this will be essential to allocating the right number of bytes. Times the number of characters in the string. It might be useful, especially when you're working with arrays of other types other than char, to pass the size of whatever object you're allocating space for. Like if you're allocating for, or if you have a type for maybe a custom type of list, an array list you've probably seen before, a hash table you've maybe seen already in Comp 2140 or are about to. But anyway, you could pass along the initial size of the thing. But in this case, we have a string, and we can assume that it's null terminated. So let's use strlen input, which is the number of characters before the end of string character. So let's do +1 to allocate space for the end of string character. And because order of operations always gets us when we least expect it, this is probably strlen input chars plus 1, which will work because char is only 1 byte large, but would break for other types. So let's add some brackets. Again, not necessary here, but good habit building.
I have a question.
What's up?
Do you generally need to reserve an extra space for the null character?
Yeah, like it's a char like any other, even though it doesn't count towards strlen. So yeah, you need however many characters you want plus 1.
I have a question as well.
Yeah.
Don't you have to do a myString arrow contents so that you can teach?
Yes, you just prevented a compiler error. Thank you. I think I'm used to writing constructors for classes, and then I wouldn't need to use that dot or arrow notation. But enough excuses. This memory allocation still works without knowing the size or length of contents, because contents is just a char pointer. malloc size of string just needs to allocate enough space for an int and a char pointer. And everything else should work exactly the same as before, but the compiler will be the one who decides that. Also note that I've totally ignored the advice I gave, not even advice, more like command, that heap allocated memory needs to be freed manually. We'll get to that later, basically right after this. Oh, yeah, okay. Wait, what was it again? Uh-oh. This library file is called string.h. We might be in big trouble. And by big trouble, I mean renaming a couple files, but still. Oh. Let's see if the compiler is able to use the brackets to tell apart string.h, as in the thing that defines strlen and stuff, and string.h as in this example. I genuinely don't know what'll happen. I don't usually redefine strings in my own programming. Looks good so far. Let's see if it actually compiles the main part and runs. I guess we could verify for sure that it works correctly by using the Clang option to show preprocessor output, and then verify that both the massive C library string.h is there, as well as our thing. But I think that if what I'm about to press enter on works, then the header inclusion worked. Cool. Cool. Phew. So we've had a lot of fun with malloc. We just used it in two different contexts. One was to aid our quest to hide implementation details for the sake of making it way easier to work on big projects. And then we also used it to define an array's size at runtime, which avoided wasting space, as well as stopped or prevented errors from, or that would result from the string being too long. Even if you caught that error, like had an if statement in the constructor that checked that the string's length was less than 500, I guess less than 499 to keep space for the null pointer, it would still be a bummer. And it's great that we're able to allocate memory of any size now. But the fun's over. We need to put away our toys, which in this case means that we must explicitly deallocate the memory that we've used when we're finished. So we haven't looked at C's file management tools in this course. We basically eschewed them in favor of input redirection. But when you're working with files explicitly, you use fopen to open the file, and then you have to use fclose to close the file. Otherwise, your operating system will think that that file is still in use and do dumb things like prevent you from moving it, prevent you from copying it, maybe even prevent you from turning off the computer. Big hassle. And it even works that way in languages with more safety features because a file is a file. Any resource we acquire needs to be returned to the OS because it doesn't know whether we're going to use it again or if it's truly gone. So to return dynamically allocated memory, we're going to use free. Very simple interface. Just give it your void pointer that you got from malloc, pass it to free, and then you're done. This is a pretty great example of hiding implementation details because if you think about it, this is probably pretty complicated behind the scenes. Malloc and free must be using some sort of table of memory addresses and how much space each allocation takes up at these memory addresses. Probably needs to maintain a table of those, and part of maintaining is expanding and reducing the size of the table dynamically, so it might have to use itself. But we don't need to worry about that. We don't need to know about this hypothetical table, if that's even how malloc and free are implemented, in order to use it. We just pass it a pointer and go on with our day. So how does this apply to us? We're familiar with the concept of a constructor because, like, that's what you do when you make objects in object-oriented languages. But in C, where you're forced to think about memory and stuff, you also need to provide a destructor, which deallocates all the memory that you took for yourself in the constructor. So the last change we're going to make to string.c is to just manage our memory. Especially since at this point, we just don't free up any of the memory we allocate. And you can imagine the memory that we're hoarding adding up over the course of the runtime of a larger program. Maybe it's an app that your user keeps open for a while and it slows down over time until they go into that multitasking menu and swipe it away. Or even worse, we could have code like this on a server that provides a website for a whole bunch of users, and then when it reaches the limits of its memory, it might crash and cause an outage. So even though it's just our little toy example here, we're learning programming practices that are super useful, more like required in larger software. I'm going to be saying that again and again in this course. So let's change the interface first this time. Oh, we're not going to return a string. We're going to destroy a string. So that's the interface to our destructor. We're just going to take the string and deallocate its memory. Occasionally, and I think you have to do this in a later assignment, like assignment 3, instead of returning nothing, you'll return something like an int or an enum to indicate whether the string was able to be destroyed. Not sure if free can fail, but you will have to use status codes of some sort for other operations. I'm just pointing that out and saying that for now, we're just going to use void to keep it simple and focus on malloc and free. Command C to copy. Oh, yeah, I haven't saved. And then we're going to put it next to the constructor. I for insert, Command V to paste. Hopefully you can follow along on other systems. I think Windows Terminal is smart enough to tell apart Control-C as in copy from Control-C as in stop running the current program. But I don't know. Your mileage may vary. Oh no, I did something wrong. No one who's calling destroy string actually has access to a capital S string. We need to use a pointer instead. And I'm just going to make that same change to the interface before I forget. A question?
For the malloc,
Mm-hmm.
you added one to the length of the input.
Mm-hmm.
If I enter 5 characters and I do string length, will it give me 5?
Yes.
So if I'm accessing the array, it's going to be 0, 1, 2, 3, 4.
Kind of.
1, 2, 3, 4. Because I don't see the need to add 1 when you can just use the last one to hold the end character.
Yeah, so the
Possible to test it without the +1 to see if it'll run.
I could, and I think it will run because we're just telling it to allocate only enough space for the visible characters and not give space for the end of string character. But then, this line will write the end of string character to the index immediately after the thing we malloced. So then we'd be writing to memory that we don't actually own, which can cause all manner of negative effects, like overwriting stuff, segmentation fault, that sort of thing. So does that answer your question? Cool. Yeah, I think I'm just going to go ahead with implementing the destructor because removing the +1 will more than likely still work in our case, but be error prone in general. So string star self. And let's implement that destructor. It's common practice to put it next to the constructor because those are the main functions for managing memory, but on a technical level, it doesn't matter. So this will amount to a bunch of calls to free. So let's free self. We did it? We did not do it, because even though we freed up space we freed up the space allocated by, or for these two things, the contents pointer still points somewhere. We also need to manage the memory that we allocated here. In larger types, this becomes a bit of a puzzle where you have to figure out what's pointing to what and try to deallocate stuff in the right order. Luckily for now, it's pretty simple. String contains contents, so we free up contents and then free up the string. And it's yet another interface versus implementation moment. If we exposed the implementation details of our string struct, we wouldn't even have to make the destructor, which would mean that the user would have to figure out this little puzzle. User as in the coder who's working with this code. But hiding the implementation details sort of forces us to keep things simple. So let's start compiling stuff again. Good. Oh my God, no errors. Oh wait, I should probably use the destructor, shouldn't I? We're not done yet. Simple as that. We solved memory management. Yippee! So, what did we just do? We put away our toys. This memory management stuff applies mostly to languages like C. It'll be useful in this course, obviously. If you're ever working on high-performance software written in C or C++, you'll also have to use this directly. Although C++ does give you some extra toys you could use that make memory management easier. But in general, in the real world, most of your memory will be managed for you, but you still need to know these concepts to work with resources managed by the OS that you still have to free yourself. So files are an obvious one, and there's also sockets for internet connections. Distributing computing gets wild. And pipes between processes, and probably a bunch more that just don't come to mind. So all this memory management stuff provides good practice for resource management in the real world. So let's see. We have 10 minutes left, so I'm totally going to get started with the next big thing, but really, that just now was the cutoff for the test. if I manage to like blaze through these slides, I might ask you like, what's designed by contract? But yeah, this is the cutoff for the test. So, design by contract. This is a tool we're going to learn over the next few lectures, and that you're going to use intensively on future assignments to prevent programming errors. It's not language specific. We're using C because its lack of safety features forces you to focus on writing good code. But you can, and quite possibly should, do it in any language. And it's not a tool for preventing user errors. This won't stop users from accidentally deleting all their stuff or closing a file without saving. Instead, it prevents errors that are to do with other programmers using your code and building on it. So, design by contract encodes your assumptions about the inputs, outputs, and state of your program. And we're just going to spend a while basically unpacking these slides, or unpacking these bullet points. What's a programming error? What do we mean by assumption in this case? How are assumptions different for inputs, outputs, and states? What's a state? Blah, blah, blah. Let's get into it. So what kind of programming errors can a programmer write? There are syntax errors. Maybe you're a doofus and you're trying to use dot notation on a heap allocated struct. Who would ever do that? Forgetting to check inputs. Inputs as in parameters to functions. In a rare instance where C is actually safer than other languages, Python is kind of the bane of my existence because its type system doesn't guarantee that any variable is of the type that you want. You could get around it kinda with its type hints, but it doesn't solve the problem completely. So an example of a programming error in this case is a Python programmer forgetting to check that the int passed to a function is actually an int and not a string or an object or whatever. Index and bounds errors, which we should be well familiar with by this point because C arrays are silly. You could think of design by contract as exception prevention. So C doesn't have exceptions. It just lets you do whatever if you try to index out of bounds or reference a null pointer. So DBC is less about pointing out these bad things once they've happened and more about preventing them from happening in the first place. So we should probably go into more detail on what an exception is before we try to prevent it. And a nice definition of it is on this slide. Something happens while your program is running where it can't or perhaps shouldn't if your program is technically still working, but you know it's accessing memory that it shouldn't, where it can't or shouldn't proceed. So maybe you're expecting an object, but its value is null pointer exception. File-related issues, so file not found exception. Division by 0, arithmetic exception. Index or bounds errors, array index out of bounds exception. Exceptions come from a violation of the assumptions we talked about earlier, usually. And there are three main places where our assumptions can be violated. Before we start processing data, so at the very beginning of a function call. After we finish processing data, so a function's return statement, or just its last curly bracket, and the state of an object throughout execution, which doesn't really mean throughout the runtime of a single function, but rather the runtime of an entire program as the object is passed around and modified. So we'll look at some code snippets and get a better idea of what I mean by assumptions, and see what assumptions we're making about inputs and outputs. So perhaps we have a function to make a string, takes a char array and a number of and the number of characters in the string. So if we just use this without much error handling, we're still making quite a few assumptions. We're assuming that num chars is greater than or equal to 0 because you can't have a negative string. You're assuming that characters is not null, that your char array actually has chars in it. Can characters equal null? Pretty sure. Nice. Anyway, we're assuming that characters is a valid C string with a null byte at the end. And that's it for input. For output, we're assuming that we're returning a valid string instance whose contents are equal to characters and which has a null byte in the right place. And again, the length is non-negative. And we have similar examples here. But I think we're going to stop here. I think I've made a decent introduction to sort of the ideas behind design by contract. We want to make sure, or actually check these assumptions in order to prevent errors. And basically shove this out of your brain for the rest of the week. Study hard for the test, and then put it right back into your brain because it's going to be super important later. So that's all for now. I'll talk much more about the test tomorrow, and for now, good luck.